At the top, you see kind of the general instructions about your exams this semester. You can bring a note card with you, a 4x6. And I tell students, if you don't have 4x6 note cards, just bring a piece of paper that's 4 inches by 6 inches and write on both sides. Notice that you have to handwrite your card. You can't type it or something like that. So the chapter one of the things we talked about was branches of physical science. I'm going to emphasize physical science. Okay, I give you a big hint. Okay, biology is not a physical science. It's a wonderful science, but it is not considered a physical science. Okay, physical sciences, remember, were the topics we're covering. Physical science is physics and chemistry and astronomy and meteorology. Key aspects of the scientific method. I guess I would emphasize there, remember, first you have first you have observations, right? And then you actually, based upon your observations, come up with some sort of hypothesis. That's like your best guess. And then based upon your hypothesis, you design experiments, so experimentation follows that. And then basically it's kind of definitely a loop. You do those three things a lot, okay? And if your hypothesis survives, then it is elevated to what? A what? A theory. Dun, dun, dun. Yeah. So kind of know the difference between hypothesis and theory. And 5 main metric prefixes. Let's see if we can remember them. Of course, we had on the small side, we have, let's kind of zoom in here. On the small side, we have centi. Even smaller than centi is milli. Even smaller than milli is micro. Seems like so long ago we talked about these. Okay, centi is 1/100th. Like cents is, there's 100 cents in a dollar. A milli is 1/1000th. And a micro is 1/1,000,000th. And then there were 2 big ones. The one I usually tell students is kilo. I was thinking drugs, I think a kilo, right? The prefix kilo means 1,000 times. And I think the other one, was it mega or giga? Mega, okay, thanks. Mega, and that must mean 1,000,000 times? Or is it 1,000 times? Yeah, it wouldn't be 1,000 times, that's kilo. Yeah, 1,000,000. Final answer. Mega. You know that one's not going to be on the test, right? So those 5 main prefixes. The next one is the standard units for length. Seem reasonable, it's meters. Okay, length and distance, oops, sorry, that got on there twice. So scratch out distance. Distance is also meters if you want to put that. I was in a hurry. What's the standard unit for time?
Seconds.
It is seconds, very good. Standard unit for mass? Kilogram, perfect. I think that was like a homework question. If you put gram, it's not quite right. It's kilogram for some reason. And then I do have one problem on there where I'm going to have you round. Remember we talked about rounding to the fewest number of digits? Okay, so for instance, I guess if I gave you the number 350.792, okay, 350.792, and I'm like, give me 3 digits. So kind of like what we've been talking about in class, you would go 1, 2, 3. Okay, so what would we round it to? 351, exactly. Okay, and that's kind of what your test question is going to look like. Okay, that was chapter 1. Chapter 2.
You want it to be like what my notation is 3.51 times 10 to the second.
Correct. Yep. Heather's saying if I wanted that in scientific notation, that number would be 3.51 times 10 to the raised to the second power. Yep, it's the same thing.
Well, I was asking, is that how you want it on the test, or?
The particular example I have, you don't need to put it in scientific notation.
Okay.
Yeah, and actually, according to Hoyle, like the whole science community, those two numbers both mean the same thing, and they both have 3 digits, so that's perfect.
Okay.
Yep. Yep. Then we talked about speed and velocity. Now, you guys remember velocity has direction. That's the big difference there. And then we talked about acceleration. So velocity has direction. This is getting kind of messy here. That's like zooms in. Oh my gosh. Direction. Okay. So what's acceleration? You guys remember?
Isn't that when you add like a direction?
Velocity is when you add a direction. And what is acceleration? So velocity is direction plus speed.
Acceleration is when there's a change in the speed of an object.
So velocity is direction plus speed, and acceleration is a change in
The speed.
the speed. No, well, it could be.
What, change in velocity?
Change in velocity. Yeah, acceleration is a change in velocity. Does that make sense, Cammie?
Mm-hmm.
I'm going to choose a different color. I'm tired of those colors. Let's choose green. Okay, so acceleration is a change in velocity. I'll just put change in V for velocity. Ooh, that color's not very good, is it? Okay, so acceleration is a change in velocity. So acceleration could be either a change in direction and or a change in speed, right? Let's choose purple. So change in velocity, let's make it a smaller stylus. That could be change direction or speed, and or speed, and or speed. Now you see why I have all my stuff in PowerPoints, because that writing is terrible. Okay. But here's where we said, like, if you're doing a circle, like if you're moving in a circle and the speed's the same, but that just going in a circle means that you're actually changing your direction. All right. So units for time are seconds, probably, right? You guys, I'm not going to have you do any conversions. Remember, we kind of fought that silly battle when we first started. So in the metric system, we said distance or length is meters. So that's what your distances are going to be. Even like how long or the distance of a wavelength is going to be in meters. Okay. So speed would be meters per second. Okay. And then acceleration is meters per second, or meters per second squared. Now, you know, these are things you might want to get on your note card. So, like, I'm going to be, when I grade your work, like for that last section for your test, I'm going to be looking for you to use units as you work the problem and on your final answer. And just do the best you can at rounding, okay? So always include the units. That last part, that last page, where you're working the problems or whatever, the problems will be worth like, I don't know, 3, 4, 5 points a piece. So I can kind of nickel and dime you if you don't use units, even if you get the right answer, okay? Okay. Good. All right, so falling objects go faster as they fall, okay? The 9.8 meters per second squared means that after it's fallen 1 second, it'll be going 9.8. Oh, wait, you guys used, yeah, 9.8. My other class, astronomy right now, we're kind of overlapping, and they use acceleration due to gravity of 10. Okay, so in 2 seconds, it'll be 9.8 plus 9.8 meters per second, right? Whatever that is, okay? 19.6 meters per second. So that's what that means. And if you want to, maybe I'll just, let's see, how would I say this? In 1 second, it has a rate of 9.8 meters per second. And at the end of 2 seconds, it will have a rate of 19.6 meters per second. In 3 seconds, it'll have a rate of whatever 19.6 plus 9.8 is. Okay? Faster and faster. Assuming that air resistance doesn't give it a terminal velocity. It maxes out. So falling objects accelerate at the same rate. I think this is a multiple choice question. It just means, and if you kind of pictured the whole on the moon thing, dropping a hammer and a feather, that's really true. I didn't bring that video in for you yet, but if you take away air resistance, objects will fall at the same rate. Okay, they really will. It's hard to prove here on Earth. Actually, here on Earth, I've seen it demonstrated like in a vacuum, like you suck all the air out of a glass column, and then at the top of the glass column you release like a penny and a feather, and they will both fall. They will both hit the ground at the same time. Okay, so I don't have much to add. If you want to put feather and hammer or something like that, that's my point there. They will hit the ground at the same time. How's that? Falling objects accelerate the same rate, and they will hit the ground at the same time. Smiley face. Okay, so in chapter 2, I went ahead and picked out 2 problems, and I went ahead and just gave you what I'm looking for exactly. So let's see what formula we need to work these problems to make it on your sheet. The first one, I will give the distance and the time, and you need to calculate speed. Okay, so for the first one, let's see, what color shall we choose? We haven't done red. Okay, red seems so evil. Okay, so for this one, to me, you need speed is equal to distance divided by time. I'll just put d over t if that's okay. Okay, so take your time working them. On your test on Thursday, you'll have 2 hours to take it. But it's really meant to be taken in like 50 minutes or so. So, you know what I'm saying?
So are we allowed to leave?
Oh, yes, you are allowed to leave. Turn it in. And I would like you, so I'll give you the test booklet and also give you a Scantron sheet so for your tests. And so make sure you put your name on both of those things. And also go ahead and give me your note card, and then I'll give you your note card back when we go to test. Okay, so that looks pretty good. The next one, given time and acceleration, calculate final velocity. Now, we just did it up there a minute ago when you drop an object. We said after 2 seconds, it's going to be going 19.6 meters per second, blah, blah, blah. And I can't remember what that one looks like. Let's see. Final velocity, v sub f. So I would have to double check this. V sub f is equal to, is it just time times acceleration? The time it falls times the acceleration. That should do it. We can test it by what we did up above when we drop an object. So when we took 2 seconds, okay, we took 2 times 9.8 meters per second squared. Okay, so this is right. I'm pretty sure this is right. Okay. Right? So in this case, I will tell you the acceleration of the object. It may not be falling. It may be somebody may be hitting the gas pedal, and they keep accelerating at this constant rate. And I will tell you how long they are accelerating, and you have to tell me what their velocity is. All right. Chapter 3. Newton's 3 laws of motion. His first law of motion is sometimes called well, do we want to review those right quick? Kind of jog your memories. Okay. Newton's first law, just put first, okay, is basically an object in motion will stay in motion. I'll put OBJ for object in motion. Stays in motion. To keep going back to move that. Okay, and I like the first law also. It says an object at rest. I'll put at rest. Stays at rest. Unless acted upon by an outside force. Goodness. Hope you guys can read that. I should have been a doctor. Unless acted upon by outside force. I'm going to go ahead and add something. I'm going to switch from color red to actually the color blue. I should probably be clarifying what sort of force, an outside force. It needs to be acted upon by unbalanced outside force. To be correct, by unbalanced. When I save this recording, I'll save the video and also I'll be able to save the sheets, I think, as PDFs and push them out there on the Twitter, on the Google, on the Facebook. Okay, so that's his first law. His second law is a lot easier than that, and I think I do have a problem I'm going to bring in for that. Let's choose purple. Second law, basically we could say F is equal to ma. Whew, that's a lot easier. Okay, so you could look at it a few different ways. You could say I apply an unbalanced force. There's some sort of force in play, and it will result in acceleration, okay, according to the mass that is being applied to. Okay. You could say, I observe an acceleration, what sort of force is at work, that sort of thing. So that's pretty good. The third law, okay, is that for every, I would do it like this. I'd say F, no, I can't do it that way. Okay, this is basically, for every action, there is an opposite and equal reaction. Goodness. For every action, there is an opposite and equal reaction. Okay, and I guess I'm not gonna do it here, but I'm gonna leave you to it because this is kind of how the test question goes. You want to be able to give an example. Okay? You want to be able to give an example, question mark of each. I'll let you guys ponder that. So inertia, actually I'm going to put Newton's first law equals N for Newton's first law. Okay, inertia is a function of velocity and mass. So under inertia, I'm going to put velocity and mass. The force of gravity is equal to G, that's that gravitational constant, times M1, M2 in the numerator divided by R squared, where the M's are the masses and the R here is the distance between them. I know it sounds like radius, but it's really kind of distance. Distance that separates the centers of their masses. Distance for R. R. So then we get to the couple of problems there. Okay, let's see. First one, given mass and acceleration, calculate force. So you're going to use Newton's second law, right? For this one. F is equal to ma. And actually, for the next one, given force and mass, calculate acceleration. You use the same one. We can do that. Don't forget your units, okay? And they'll already be in the base units and everything, so that'll be good. Bless you. All right, on to. So define work. Oh yeah. We talked about a couple different types of works. Remember that guy moving the crate? Okay. In that case, and it's a capital W, right? A big W is equal to the force that that guy applied times the distance he applied it. That was the work. We also said that that was kind of pushing horizontal, and that was ignoring the force of friction and everything. That was kind of a, but we need to do that. The other type of work is like if you lift something, you are actually working against gravity. So in that case, the work, I'll put little g here for against gravity, okay? The force you're working against is actually the mass of the object times the gravitational constant here. And in this case, you're relocating it horizontal or vertically. And so we take h is kind of how you displaced it. So that's the work there. Seems like you guys did some of that in your lab. I don't have any specific questions on the test, I don't think, from your lab, although we did some really good problems in lab. Power is, then you take work divided by time. And you guys did that in lab too. So power, capital P, is equal to work divided by little t, which is time. And I don't have it on your review sheet, but let's just go ahead and jot down what the units would be for work. So what are the units for work? Joules, very good. Units for work are joules, capital J. What are the units for power?
Watts.
Watts. And I couldn't remember, is there an abbreviation for watts? Is it just?
There is a capital W again.
It's just a capital W? Oh, you're right. I hate that. I would spell the darn thing out. Capital W for watts, for the units. Very good. Perfect. So, actually, you see, I'm jumping ahead, but you do have a power problem here, okay, for this chapter. Okay, so potential energy, PE versus kinetic energy. Potential energy is stored energy, right? PE is stored. Sometimes they call that stored energy energy associated with position. Okay, stored energy, I'll just put position. I can really see the whole position thing if you think of the potential energy of something that's just hovering and could fall potentially. Okay, that's potential energy. And then kinetic energy is associated with motion. So KE is associated with motion. Continue. Okay, so does this look familiar with the whole little bullet? You plugged in for the bullet and you plugged in for the boat, yeah. The next one, consider a swinging pendulum, and we didn't really talk specifically about this. We did indirectly. So, for instance, let's see, how do we do this? Let's go ahead, and this actually is a ceiling. We hang a pendulum, okay, from a string, and then we go ahead and start it moving, okay? And if you can kind of picture, it's going to go up, okay, going to stop, and then it's going to go. It's like a swing, right? Okay. So actually, the deal here is once we start it swinging, okay, can you see where up here, when it's up here, okay, it has the most amount of potential energy? I'll say PE is greatest. And I don't know if you can kind of go, and like if somebody's on a swing, the fastest they're going is like when they're right there by the, okay? So if it's going fast down here, it's going to have the most amount of kinetic energy, most KE. Okay, then take a look at the problems there. Given mass and velocity, calculate kinetic energy. Well, I just wrote it right next to that, didn't I? Okay, so this is the one. This is like what you did for your homework. So I'm going to just refer to this equation. If you have the mass, you have the velocity, you can knock out kinetic energy. Okay, easy, 1/2 mv squared. The other one down here is given force and distance and time, calculate power. So it's kind of a combination of these. Okay, so power is equal to work divided by time. Work divided by time. Okay, and work, one way of talking about work is force times distance. So we could actually substitute in, F and times D up there, divided by T. That's your power. Okay? And then the last chapter, we talked about 2 types of waves. We talked about, I didn't use the word parallel or perpendicular, but I think I will right now. Transverse waves, the wave is going this way, but actually the movement goes, what we say, perpendicular. The movement goes perpendicular to the direction the wave is going. Okay, so actually this is perpendicular. And I'll just put a capital T for transverse. Hope you're okay with that, because I'm getting impatient. And what sort of sound or light is like that? Which one? Light. Yep, light is like this. Actually, in a minute, I'm going to say light, and sometimes people use light for all of the cousins, but light is like electromagnetic radiation. And then the other one goes like this, where it has compressions and rarefications, and compressions and rarefications. Okay, that's like the slinky, right? And that one is, I'll put L for longitudinal. L for longitudinal. And I'll put the word parallel. So in this case, the direction actually is parallel with the wave itself, with the compressions and the rarefactions. The next one, and actually the frequency, wavelength, velocity of waves, let's see, how do I say this? Well, just on it's easiest to kind of talk about the transverse wave. Wavelength, of course, is you could go like from crest to crest, and that would be your wavelength. The variable for wavelength is lambda. The variable for frequency is f. And of course, the variable for velocity is v. And let's see, let's go ahead while we're up there, and I'm going to write under frequency, what are the units of frequency? You can actually, hertz, you can actually use 2 as far as I can tell. You can either use hertz, which I think is really convenient, or per second. Either one, it's the same thing. What's the units for wavelength? It's a distance. Meters, very good. And what's the units for velocity? Meters per second, perfect. So let's go ahead and knock out what the relationship is between those 3 things. So we said, I think the easiest way for me right now to remember it is velocity is equal to wavelength times frequency, or frequency times wavelength. Velocity is equal to wavelength times frequency. And actually, the 2 problems associated with this, you're going to want to have that either here or there, velocity. Okay. The next one, I was thinking about how to kind of show you. I'm going to, down here at the bottom, actually, I'm going to write these cousins. Because I would, on my note card, so I wouldn't have to think too hard, I would do something like this. I would write gamma Gamma, R for rays, X-rays. Then we have ultraviolet rays, UV. I'm kind of abbreviating them here. Visible. And then after visible, we have infrared. And then we have micro. I'll put micro W for microwaves. And then we have radio waves. So let me go ahead and kind of put boxes. Gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, and radio waves. And just for kicks, it might be helpful to kind of take the visible light, since that's so important to us, and kind of expand it. So visible, actually, you can do the Roy G. Biv, but in this case, you're going to have to go backwards. So it goes red, orange, yellow, green, blue, indigo, and violet, kind of that way. Do you know what I mean? I did the Roy G. Biv backwards. That's my visible light. Okay. And then the other thing that might help you is that if you have all the cousins listed like this, of course, most people would tell me that this is the high energy, high E for gamma rays, and this is the low energy. We didn't talk too much about that, but what we did talk about is wavelength. So over under gamma rays, do they have a long wavelength or a short wavelength? Short. Very good. Short wavelength. Short lambda. So over here, or in a radio waves, I'm going to put long wavelength. All right, now we need to say something about frequencies. Gamma rays, do they have a high frequency or low frequency? High frequency, exactly. Did that just like turn around? Oh my gosh. As you tell it, high F for frequency, okay? And this has a low F for frequency. So I would probably put something like that on my note card. You have till Thursday to get it ready, so. All right, the next one, actually, this one came from a homework question. I'll put HW next to the speed of light, okay? Because one of the things, I didn't talk a lot about it, but there's something called the index of refraction for diamonds. And so, for instance, for diamonds, it's like 2, which means that when light travels through a diamond, it like slows down by a factor of 2. It slows down. Light slows down. And the thing is that light goes fastest in a vacuum. The speed of light, that 186,000 miles per second that some of you guys may have memorized, that is in a vacuum. It goes slower anywhere else. Okay, so how would I say it? Speed of light in a vacuum is fastest. And if you want to, for medium, if you want to put the word diamond, I don't know if that's what the test question is, but for instance, diamond is a medium that light travels through. Range for audible sounds, I'm going to put HW next to that one too. I don't have a homework question like you guys answered for like converting, I don't know, frequencies into wavelengths for the audible sounds. And I don't even have it handy, but is it like the ultrasonic starts at 20 kilohertz? Does that sound right? Okay. So let's see, range for sounds. 20 kilohertz is like the highest one you can hear. And then it's like 20 hertz is the lowest one you can hear. 20 hertz. Good. Together we got that done. The Doppler effect, okay. This is a key for the Doppler effect is you need to have a moving source. Now when I say source, I mean something that is emitting a sound or a light.
So like the car.
That's like the car. Yep, moving source. I'll put car here. That's good. And you just want to review if something's coming towards you. The wavelengths are going to be squished, okay? Shorter wavelengths. I'll say moving source. I'll say toward equals shorten wavelength. I'm running out of room. I'll change colors into blue, okay? And away gives you, lengthens the wavelength, so I'll put long wavelength. And then the last two, notice that you are going to be using, and we'll go ahead and put it again, the velocity of a wave is equal to the wavelength of the wave times the frequency of the wave. Okay, so just remember though, velocity is in meters per second, wavelength is in meters, frequency is in hertz, or per second if you want to. First one, I give you the wavelength and frequency, you tell me velocity, you remember speed, velocity. And then the other one, I give you the wavelength and the velocity, and you tell me frequency. Okay? So it looks like we're set for Wednesday, kind of dabbling in chemistry a little bit.